transactional and analytical databases with MySQL and ClickHouse. My name is Stig. I work for Huawei's Cloud Database Europe team in Trondheim, Norway. I have a background in a few years of data engineering and lots of developer tooling, and you know, I'm more like a generalist. By no means a database specialist. I've been a user of databases most of my career, so this database specialization is a new field for me. Nevertheless, I've been had the chance to work on a very interesting project for Huawei on this ATAP product since December. Just to go through the agenda for this talk, so I'll start by explaining a bit about the motivation for the project I'm presenting. Then I'll go a bit into how ClickHouse works for those who are not familiar with it. I'll talk a little bit about also ClickHouse combined with MySQL as a replication slave, if you will. Then I'll say something about what our users expect from an HTAP solution. And then I'll go into the challenges we have come across with ClickHouse in this setup and how we solve them, and finally present our implementation. So the group I work in also develops Taurus, which is a cloud optimized MySQL managed service, similar to Amazon Aurora, for example. It's also known as Ghost DB for MySQL. Our customers keep asking for HTAP solutions, so this is our way to start working into that product field. Our team had some experience with ClickHouse already. There was a recently added database engine called MaterializeMySQL. That seemed like a reasonable starting point. So we took that as a basis, and we were confident enough that we could adapt this code base to our needs. So we started the Orion project in January this year, with the aim of at the beginning, implement a proof of concept for pilot customers, and then move on from there. So a little bit about ClickHouse. So ClickHouse is maybe 4 or 5 years old. It's a fairly new database. When I say modern OLAP database, it means it is built with a different philosophy than some of the more traditional ones, like Sybase IQ or Oracle Exadata. So ClickHouse was basically built from a very simple foundation, where the idea was to see how much performance they could get out of modern hardware. So things like vectorization and parallelism and using modern SSDs and so on was part of the design from the beginning. And then the project has matured over time, and it has become more streamlined. The SQL support keeps improving. So it's sort of built from the bottom up and not top down. The main table engine in ClickHouse is the merge tree table engine family. I say family because it's actually a bunch of different variants. We'll talk about 2 of those today. The merge tree table engine has immutable tables. They are append only, which you know, leads you to understanding that updates and deletes are not straightforward. They are basically asynchronous batch operations that require background merge before the changes are visible. Another thing to note is that primary keys are not a unique constraint. You can insert many rows with the same primary key. Nothing stops you from doing that. And if you want to enforce uniqueness, you have to do that at query time, basically in your query yourself. There's a variant of merge tree called the replacing merge tree that makes this slightly easier, but it's still not 100%. So we'll get back to that. Yeah, and ClickHouse has very different trade-offs compared to your traditional OLTP databases like MySQL. It's eventually consistent. It prefers, inserts in batches with thousands or maybe 100,000 or as much as million rows per insert, and it performs better if you have bigger batches to operate on, which is natural for a column-based database. And one of my favorite things about ClickHouse is that it has a really large set of integrations with other systems, including HDFS or S3 for storage. You can query objects in HDFS or S3 as if they were tables. You can also add the remote tables for MySQL, and then you can join between ClickHouse and MySQL tables. Same thing with Postgres. Yeah, and you can also pull data from non-relational databases like Mongo and Redis, and also stream events from Kafka into a ClickHouse table. There's also an embedded RocksDB implementation, which is still a bit basic and I guess early days, but lots of interesting things happening. And there's still a ton more integrations that I didn't mention in this talk. So merge tree tables are structured in partitions. When you create the tables, you have to tell, in your schema how you want things to be partitioned. Otherwise, it's going to be just one big partition. The partition itself is organized into parts. The parts, and then the naming here is a bit funny because partition and part, it's easy to mix them up, but they are very different things. So the name merge tree comes from the way parts are combined over time. If you insert 10 rows at a time, 10 times, so you get 10 parts, and then 2 of those will be merged, and the next 2 will be merged, and so on, and until you have 5 parts, and then this process keeps going until ClickHouse has determined that the part size is good, it's optimal, potentially creating just a single part within the partition. That depends on the number of rows and so on. So the tree part of the name is really about how these background merges combine chunks of your data in a tree-like process. Within each part, there's typically 1 file per column, and the elements or the data, the values within each column file are ordered by the primary key or the order by expression for the table. So the first row is going to be the first element in every column, and the second is going to be the second element in every column, and so on. And there's an index file on the side, which is a sparse index, which effectively just gives you a fast way to skip parts of the data files that you're not interested in. Right. In our case, we are interested in the MaterializeMySQL database engine, It is still an experimental feature in open source ClickHouse. It's a bit rough around the edges still. Yeah, that is something to consider. But the way it works is that it connects to MySQL, in our case Toros, and behaves like a replication client. And for each database, you have a synchronization thread inside ClickHouse. And it buffers rows from the bin log. When it has either enough bytes or enough rows or a certain time has elapsed, this buffer is flushed to the actual tables. And the flush basically means there's an insert executed for each table. DDL events, meaning things like alter table, create table, drop table, and so on, are converted to ClickHouse syntax. But this process adds two columns, one called _sign, which gets the value 1 for inserts and updates and value -1 for deletes. And this is how we sort of simulate deletes in the database or table engine in ClickHouse that doesn't really support deletes. And the _version field is increased by 1 every time we get a row event from the bin log, which basically means that every time there's a change, we get a new version number, and this keeps increasing. It's an unsigned 64-bit integer. The underlying storage is replacing merge tree, which is a variant of merge tree that is made for enforcing uniqueness for primary keys with some caveats. And every time this flush process happens, there will be one part in each table, maybe more, but usually it's one. And obviously, when you have a lot of inserts, like every second or every 2 seconds, that also creates a lot of background merge activity. So an important part of tuning performance here is tuning this time so that you get the right trade-off in terms of I/O amplification versus the freshness you need. So replacing merge tree, when you make a replacing merge tree table, you have to tell it which column you want to use for determining which row to keep if you have several rows with the same primary key. So in our case, we use the _version. So we always use the newest version of any given primary key. And during the merge, where the merge tree table would simply concatenate all the rows from part 1 and part 2. In this case, we only keep 1 row for each primary key value, and then we keep the one with the highest version. So this is a process that happens in background merges, but it also happens if you do select final. And that's sort of the last bit to ensure that you have at least no duplicates in the output from your queries. The drawback with select final is that it takes a lot of extra time. It's on the order of 10 to 100 times slower, typically, than a query without final. And with MaterializeMySQL, you don't have to think about this. The engine wraps the underlying tables for you and injects final and basically like a where sign equals 1 filter to remove or hide the deleted rows for you. Right. So now I'm gonna do a little demo. So let's see here now. I have to move this. Okay, so we have our ClickHouse and we have our MySQL. So we have, I've run sysbench and created 4 tables in MySQL. And in ClickHouse, I don't have this database yet, so I'm going to create database. So this refers to the so let's wait for that to go back. This refers to my MySQL instance, the database, username, password. Right. So then we can keep an eye on the replication progress here. So each of these tables has 10 million rows. So now table 4 is done, table 3 is almost done, table 2 has started. So this initial load is not using the bin log, it's actually just doing a select star. And once this is complete, it goes into bin log mode and waits for changes to come in. Okay, right. So I'm gonna run sysbench in the background here and keep making changes. So if I do a select count from SP test 1, oops. It's fairly fast, but it's still taking 1/10 of a second. Normally in ClickHouse, this should only take a few milliseconds. So here we actually see the cost of adding final to the query. So, but it doesn't add the final if you have version in your query. So this is a way to emulate that. But now we also see we get more than 10 million rows, which means that we have some duplicates in here, but it takes only 14 milliseconds. So now you see the difference in performance that is caused by final. Okay. So that's performance is one problem. The other thing is that there is no transactional consistency out of the box here. And other issues with MaterializeMySQL in the open source version of ClickHouse is it doesn't support all types like enum and time. We have implemented bit and we're probably going to implement enum. And we'll see if any customers need the time type. We also need to address the query performance, because if you start using this like you would use ClickHouse, then queries are going to take 60 seconds instead of 2, and that's not acceptable. There is a lot to be done still with robustness, failure handling, restarting the sync thread if it's stopped, and so on. There are some corner cases with the DDL conversion, especially create table like and also create table select. We have fixed those 2 in our version. There is no encoding or correlation support. We have worked around this by converting everything to UTF-8, but we don't have correlations yet. And there's also a lot of assumptions done when you convert the DDL. Typically, how you do the partitioning, and also what should be in the order by or primary key. Out of the box, the primary key is very long. It basically concatenates your unique indexes and indexes. And that gives you a very long primary key, and that's leads to reading much more data than you would have to. There's also no support for distributed or replicated tables for ClickHouse, and rows that are deleted are just hidden from your queries, but they still consume disk space. So if you have a table where you have a lot of short-lived rows, that is going to cause storage to keep increasing. So that has to be addressed manually. And finally, for each database you create in ClickHouse like this from a MySQL instance, you consume the full bin log from the MySQL database, which means you see events for every database, but it just ignores the ones that are not for the one you have configured. And if you have a lot of traffic and you want to replicate more than one database, you get a lot of unnecessary network traffic. So we took ClickHouse 21.2 and we made a bunch of changes to it. First of all, we added some transactional consistency. So we basically control visibility of changes so that you don't see rows that are part of a transaction that has not been committed yet. And then we also added a snapshotting mechanism that removes duplicates ahead of time in the background, so you don't have to do it in the query. Then we get back to pretty much the same performance that you would expect from regular ClickHouse. Our customers are willing to accept, slightly more out-of-date data if they can get more performance. So the first thing we did was to fix the MVCC support. That was a showstopper. The second thing was to get around the select final overhead. We have an experimental mechanism for modifying or giving more hints to the DDL conversion called table overrides. We fixed the missing data types as we come across them. And then we convert strings to UTF-8, like I mentioned, and then we'll do collations later. Our solution is still single node ClickHouse. In like big data or data warehouse settings, that's not great, but for combining with an OLTP database, single node ClickHouse goes a long way. So the way we did MVCC, we added a new query setting called MVCC isolation level. So you can choose in your profile or on each individual query if you want to have snapshot or if you want to have use final but have transactional consistency, or if you want it to work like today, which is still default. We needed to add a new table engine to address some race conditions when it comes to how data is deduplicated. And we needed to add a new table setting to support that. So to handle transactions, we had to add some more metadata to the database, the MaterializeMySQL database, where we basically flag the data versions that are at the end of a committed transaction. This way we know which versions represent safe points in the bin log, if you will. And then we skip between these versions when we control the visibility. And finally, we use preware to filter on this underscore version to the last known transaction boundary. so we can control visibility. And we do this consistently within, for all of the tables in the databases in a single query, even if it's lots of subselects or union all type of queries. And to do all of this, we need to keep track of which queries are consuming which, or are viewing which versions of the database. So we reuse some terminology, but not in a pure way. It's more of a naming things, to the closest thing. It's not an apples to apples comparison with the MySQL manual, for example, because they are not really the same thing. The default isolation level is the one we call read uncommitted. That doesn't mean that you see the data in the buffer. You see, you might see rows that are from a transaction that has not yet been committed. And like I said, that is how MaterializeMySQL works today. And then you have read committed, which is, it hides partial transactions from you, but it's still using final. And then finally, you can choose query snapshot. And then your query will be diverted to a different table where we have done the deduplication ahead of time. This means we use more space because we keep some duplicates of the table around, but that's still acceptable. So to do the table snapshots, we add a new table setting. So current table snapshot, if you don't have snapshots or if none have been created yet, it's going to be 0. Otherwise, it's going to be 1 or 2, and it keeps flipping between 1 and 2. So you serve traffic from one table and then you update the other one, and then you keep flipping back and forth. Sort of like frame buffers when you swap between frame buffers to provide smooth graphics. We have a new system table with the metadata exposed. And then we have an external process in the control plane that maintains the shadow database for each MaterializeMySQL database. And then we have 2 shadow tables for each of the source tables. The only overhead left is really that we still do filter on sign equals 1. But this column is really well compressed. And we typically measure, around 1% overhead. And that's still acceptable. Right. So I can show you how this works in the demo we just did. I'm just going to start the snapshotting thing. So while I do that, so we are now snapshotting the first table. That's done. So now we can do a select count from this table. And then we do settings, MVCC isolation level equals query snapshot. And then it's back to 17 milliseconds instead of 100. We also have read committed, which gives you pretty much the same as before. Read uncommitted is the default isolation level. You get the same result, only in different ways. So it's almost a 10x difference in this case. And doing select count isn't a really great way to do a benchmark, and this isn't a benchmark. It's just a way to show you, the difference in scale between the different query engines. Okay, so status and plans ahead. So we are rolling this out to pilot customers now with the MVCC and snapshot support. we prioritize based on what our customers need. And we have contributed some code back to the ClickHouse repo, but we had to prioritize the internal development. So we have to come back to sorting out what we should contribute back a bit later. But we do plan to contribute as much as we can, because when you maintain an internal fork, the less code you have to maintain privately, then the less work it's going to be also. And we want to give back to the community as well. Yes, so with that, I would like to thank you for watching. Please reach out on Twitter, preferably, or LinkedIn. And you can also see my GitHub account there. Yeah, thanks for watching. Bye-bye.